Hi everyone, today we're going to be talking about factor analysis. Factor analysis is one step further from the Gaussian mixture models that we talked about last time. Factor analysis also uses the algorithm of expectation maximization to compute the optimal parameters. If you don't know about expectation maximization, please refer to the previous video where I discussed it with the Gaussian mixture models. So what is factor analysis? Well, to do that, we first have to give a premise of what our problem is. So say we have data, x, which is in Rn space, or let's call it Rd space. D for dimensions of features, right? And say originally we said that x has a Gaussian that it's associated with, right? So what that means is if we draw x out on a graph, say this is x, and then say this is our Gaussian, say this is the mean of our Gaussian, and it radiates out like this, right? And it is more likely for x to be a part of this cluster than, say, another Gaussian that is really far away. Say it's all the way over here, right? So that just means that x belongs to that Gaussian mixture. However, when we have a lot of data, this is totally okay. But what if our data is not like that many, and we don't have enough data to kind of say we have this many Gaussians, and like we have a lot of dimensions, which is a problem. Well, recall the idea of the optimal values of Gaussian mixture models. So say mu is equal to the summation of y and k, where y and k is equal to probability of Zn given Xn, right? Actually, just to make it more clear, I'll say Zn is equal to k given Xn, because it's y and k. Y and k Xn over the summation of y and k, right? And what we had before from our GMM was that the sigma, the covariance, is equal to n y and k xn minus mu k xn minus mu k transpose divided by the summation of y and k, right? Okay, so this this gives us a d by d dimensional matrix, right? Well, what if we have say our n is less than d? If our n is less than d, or say like even the points that are in this Gaussian are less than d, then we can form a full covariance matrix. So if we have n, like the number of points belonging to that Gaussian is less than d, right? That's a really big problem. Like if you try to compute this on a computer, your computer would just explode because it wouldn't know how to do it correctly. Because you're trying to compute, let's go to the slide. You're trying to compute p of xn zn, right? And this is equal to p of xn given zn times p of zn. And what p of xn zn is p of xn given zn is equal to 1 over the square root of the determinant of 2 pi sigma times e to the negative 1/2 x minus mu transpose sigma inverse x minus mu, right? This is the probability. This is the Gaussian, but just for more than one variable, right? So what we have here is this determinant is kind of like the volume of our covariance. So determinants mean volume. For those who are not familiar with the concept of determinants, think about like if you had say a square in 2D, right? The area is defined by this x and this y, right? So it's x times y. Well, you can also say this in terms of a 2D matrix as an x, y, 0, 0, right? So this is x times y minus 0 times 0. Well, if your square looks like this, right, it might look something like a, b, c, d is equal to a times d minus b times c. And this is actually the, like if this was a, this would be the determinant of a. So when you generalize it to higher dimensions, it basically means the area of that figure that your matrix defines, right? So it's like some vectors that is kind of pointing in different directions, and you want to find out the area that it creates. You don't really need to know this too much, but if you understand this, I think the next intuition will also be very good, which is, say you have a 2D again, right? And one of your vectors is this, right? And the other vector is, say, this, right? What's the area created by this? The determinant of this A is equal to 0, right? Because the area of like a single line in 2 dimensions is 0, right? We have to have something that looks like this for it to even have an area, but we don't have that. So that's an issue. So usually in linear algebra we call this a singular matrix. A singular matrix just means that its determinant is 0, right? Well, in this case, if a determinant is 0, then that means that matrix is also non-invertible. Okay, so can you see what's the issue here? If we have nk is less than d, right, that means that we have at most nk bases for our covariance matrix. And that just means that the vectors that span out to form the area, right? And if we have like only one vector in a 2D space, the area will be 0, right? Then what do we have here? We have something 1 over 0, right, times e to the negative 1/2 x minus mu transpose times something that's illegal because we can't take the inverse of it, x minus mu, right? So this is just like two things are already wrong, right? And that kind of just like completely fucks up our algorithm here because we have divide by 0 and also we can't invert. And that's why we can't use Gaussian mixture models to kind of do this if we don't have enough data, right? In most cases, we would say that the amount of like if we don't have enough data, you should probably do factor analysis. And the idea of factor analysis is very similar to Gaussian mixture models. It's just that it's a little bit more abstract. So before we dive into factor analysis, we have to do a little bit of like understanding of some linear algebra / statistics stuff before we go forward. And I'm not going to prove it right now because it takes way too long. But there are some links online if you want to know about it. But pretty much, say we have an x is equal to a vector x1, x2, where x1 has some like, is like actually like x11, x12, dot, 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 right? And then x2 is x21, x22, dot, 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 right? So this forms a really long vector, right? And so, so we say that x1 is in, say, R space, and x2 is in S space, right? Then that means that x is just the added length of both of these, so it means that it's in R plus S space, so R plus S dimensions. Now, now we say that x is from a Gaussian distribution, where its mu and sigma are its mean and variance, then we say that then we can say mu1 is also in R space, mu2 is in S space, mu is in R plus S space, sigma 1 is in R by R space, sigma 2 is in S by S space, and sigma is just in R by S times R by S. I mean, R plus S by R plus S. Does that make sense? It kind of looks like sigma 1, 1, sigma 1, 2, sigma 2, 1, sigma 2, 2. Right, and this part is R, this part is S, this part is R, this part is S. Okay. And this is the covariance matrix. Okay. So one important thing that we should know is the conditional distribution of x1 as a Gaussian distribution. So So I'm not going to prove it right now. I can probably leave some links to show why it is the case. But mu1 given 2, in this case is x1 given x2, is equal to mu1 plus the sigma 1, 2, sigma 2, 2 inverse x2 minus mu2. And sigma 1, 2 is equal to sigma 1, 1, minus sigma 1, 2, sigma 2, 2 inverse, sigma 2, 1. And these two are very important for our proof of factor analysis. The proof is not too difficult, but it's just a lot of expanding. So it might take a lot of work to show it, but it's not like a very hard proof in itself. Okay, so let's move on to our factor analysis model. So our factor analysis model is kind of similar to what we just said with the x1 and x2s. So what we say is that we have like these z variables, and then we have these x variables, right? And this is in a vector, okay? And z is belonging to a normal distribution of 0 and I, which is the identity matrix. I just looks like 1, 1, 1, 1, 1, 0, and 0. Okay. And x given z is going to be normal of mu plus this called lambda z, and then this thing called a psi. Okay. So this is the mean of x. This is the covariance of x, right? And so what does this mean? What we're trying to say here is that z is some hidden factors, for example, of x, right? So say x is like price of the house, right? And like popularity like of the house. And then say like, yeah, sure, let's just keep it to these two for now. And then what we have are some hidden factors, right? Like square feet, right? And like say, I don't know, what else is there? Location, and like schools around it. So we can say that like square feet, location, and schools contribute to the popularity of the house, and square feet, location, and schools may contribute to the money of the house. However, maybe popularity, maybe this one is like more likely the school around it will give it the most popularity. but the location will be the most contributing factor to the house, but we don't know that. So we just say that kind of this is equal to z, and this is equal to x, right? And what we observe is x. So say we only have data that's about the money of the house and the popularity of the house, but we don't know about the square feet location in schools. So what we say is that actually usually the x's dimensions is usually greater than z's dimensions, but this is just an example. But pretty much we say that z is the hidden variables that determine the value of the x's values. And we don't know these z's, so we're just kind of trying to find them. And so to make sure that we don't run into the same issue where we have like a covariance matrix that is singular, as in its determinant is 0, therefore we can't solve for it, we kind of restrain this matrix. This matrix has to be diagonal, which means that it has like, it's kind of like the identity matrix in that it looks like phi 1, 1, phi 2, 2, but then everywhere else around it is zeros, right? This will make sure that it's positive semi-definite, which means that it has a positive area. You don't really need to know what it means, but all covariance has to be positive, right? And the mean is going to be dictated by this mu, this mystery mu that we don't know about, and this is a transformation matrix. Transformation matrix. Right. So we transform the values of z so that it becomes x, right? So say, yeah, okay, I don't think I need to give an example for this, but pretty much you just transform z into x, and so there's a special matrix that kind of creates that. So obviously this mu, you've seen it before, right? Like you learned in Gaussian mixture models that it means the average of something, right? And here we will see that it's going to be the average of x. We're going to prove that. And obviously the average of z here is 0 because it says that it's 0, right? So what we're going to do is we're going to take the expected value of x, and we're going to see that, well, okay, first let's take the expected value of z. The expected value of z is equal to 0. Because we just said it was 0 right here, right? So that's pretty easy. We don't need to think about much. Now, we have to take the expected value of x to convince us that it's actually mu, right? So this is the same as the expected value of mu plus lambda z, right? And and also we also have like a little bit of a noise, where the noise is equal to a normal of 0 and phi, right? Because this is just the noise, and this is our noise right here, the covariance, right? And so we can kind of break this x is equal to mu plus lambda z plus epsilon, which is the noise, right? But here we will just include the noise here in this term. Okay. So this, you know that additions inside of expectations can be, expectation is linear, so we can take it out. And we get expectation of mu plus lambda expectation of z plus expectation of epsilon. I took the lambda out because it's also linear. We're just multiplying, so we can take it out. And now we know that since this is a number, right? This is just a single number, and the expected value of a single number is just mu. And then we will see that the expected value of z, what we just saw here, was 0, right? And now the expected value of epsilon, that's also 0 because we just saw it right here, right? So this would be 0, right? Then that means that the entire thing is equal to mu, right? And so recap, the expectation of the vector z, x, is equal to 0 and mu, correct? Okay, cool. Now we need to calculate the covariance of this matrix, right? So what is the covariance? Well, first we need to calculate the covariance of z, right? That means it's z minus mu z. And then times z minus mu z transpose. This just is the covariance matrix formulation. And what do we know about the mu of z? This is the expected value of z, right? And this is equal to 0, right? So what we really have is just z transpose, right? And by definition, z transpose is going to be the identity matrix, because what we just said before was z is belonging to a distribution of 0i, right? And so this is the covariance. Okay, so we're done there. And now we want to know the covariance of, say, the covariance between z and x. So z minus mu z, x minus mu x transpose. And this we kind of expand it out, and we get expectation of z. Oh, and this is 0, so we just ignore that for now. We know that this is mu, so we have a constant. Z x, right, minus z mu transpose. And that is pretty much it, right? However, we need to expand this term, right? Because x we don't really know. So first we get expectation of z, and then the expanded value of x is mu plus lambda z, right? Plus epsilon transpose minus and then we can minus expectation of z mu transpose, right? Because expectation is linear. And now we know that this is 0, right? That means that this entire thing is 0. Now we can break this up into a little bit more things. So we get expectation of z mu plus expectation of z mu transpose, and then z transpose lambda plus expectation of z epsilon transpose. And okay, so now that we saw what this was equal to 0 because it's the same as this one, right? Now we know this one is 0 because both of these are 0, right? The covariance is their variance, and their variance is, and their mean is 0, right? Now, and also these are independent. Because these are independent variables. Like, z has nothing to do with the noise with respect to the other one. That's just how we defined it. Now, we have this, right? And remember, we said we could do this, right? And this is equal to I times lambda, which is equal to lambda, because I is just like 1 times lambda, so that's lambda. So we got lambda here, right? One more thing is, just one more thing is the expectation of x minus mu x minus mu x transpose is equal to the expectation of, and then we just do FOIL, right? So it's just x transpose, right? Let's see, minus mu 2 mu x transpose plus mu x transpose, right? Okay. However, this can be done in a little bit simpler way. You can do this, and then we can expand and see that it cancels out. But you can just expand right from here. So you know that x is equal to mu plus lambda z plus epsilon, right? Then you can make this into, like, this mu and this mu cancel out, right? And this mu cancels out. So you get lambda z plus epsilon, lambda z plus epsilon transpose. And this, you do FOIL again, and you get a simpler term because now it's just like you know what the variance of these things are. So you get lambda z, z transpose, lambda transpose, plus 2e lambda z epsilon plus e transpose, right? Now this one's actually pretty easy because we just saw that this, right? This is the same as e z epsilon. Oh, sorry, I forgot the transpose. This is equal to 0. So this entire thing is equal to 0. Now we know that this is the covariance, is the variance of epsilon, and this is 0. Actually, the epsilon is equal to psi, right? It's the variance, and that's how much x varies, right? And so that's psi. This is equal to lambda e zzt lambda transpose. This is equal to lambda I lambda transpose equal to lambda lambda transpose. So we can see that the variance of x here is going to be equal to lambda lambda transpose plus psi, right? Just to recap, the expected value of z z transpose, or this is equal to the variance of z, right? Is equal to I, right? Now the z x minus mu x t thing, this is the covariance of z and x. This is equal to lambda. And then finally the variance of x is equal to lambda lambda transpose plus psi. Okay, so why did I say all of these things? Okay, so I said all of these things because we need to use these in our expectation maximization algorithm. We need to use these values to kind of compute what is the best answer. So, so what we have here is that this is everything we need to compute sigma. Do you see why? Because sigma is the variance of these variables, right? And so this is just equal to, and then you know that this is z, this is x, this is z, this is x, right? So this is I, this is lambda, this is lambda, this is lambda lambda transpose plus psi. Okay, so to recap, we get mu is equal to 0 mu, and sigma is equal to I lambda 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 transpose plus psi. So recall what we just talked about last time in expectation maximization. Expectation maximization. We talked about trying to maximize, first finding the expected likelihood and then maximizing it, right? So what was the equation? It was like this. It was like we sum over all n, we sum over all zn, right? And then we have this mystery distribution qzn, right, times log of p of xn zn qzn, right? And we found out that qzn is actually equal to p of zn given xn, right? That's what we talked about last time. Go review that video if you don't remember this. So what is p of zn given xn? Okay, and to compute this p of z and xn right now is actually very difficult. However, we just talked about that one thing that I didn't prove, where you can use the conditional, you can find the conditional Gaussian given the original parameters, right? So what is the conditional Gaussian? The conditional Gaussian is mu of zx, right? It's the normal of mu of zx sigma of zx, right? Is equal to the probability of zn given xn. And how do we get these things? Well, remember what we just said before about mu of 2 given 1 and sigma of 2 given 1 is equal to some mumbo jumbo that we wrote down. Well, refer to that, and what we get is this expression, which is for mu1 is equal to mu1 plus sigma 1 2 sigma 2 2 inverse x2 minus mu2, and then for sigma it's equal to sigma 1 1 minus sigma 1 2 sigma 2 2 inverse sigma 2 1. Okay, so what does that mean in our case? Well, actually, it doesn't really matter whether you want mu of 1, 2 or mu of 2, 1. Does not matter. All you need to do is flip the numbers. So wherever there was a 2, you make it a 1. And wherever there was a 1, you make it a 2. And vice versa. So if you kind of just replace these 2's with z's and x's with 1's, right, what we get is you get mu of z given x is equal to lambda transpose lambda lambda transpose plus phi negative 1 x minus mu x, right? And then for sigma z given x is equal to I minus lambda transpose lambda lambda transpose plus 5 negative 1 times lambda. You can see that I'm going to just circle these things to make it a little bit clearer. Right now, mu1 is 0. So that's why we don't have that term here. And sigma 1, 2 is equal to this. And sigma 2, 1 is equal to this entire thing. x2 minus mu2, as you can see, is this. And then the rest you can figure it out on yourself because, I mean, it's the same thing. Okay. So now that we have this, we have the ability to compute p of zn xn, right? So now that means that our E step is good. And I think we've done enough derivatives right now, so I'm just going to give you the answers for the m step. You can work it out yourself if you really want to. But yeah, let's just write down the m step. Actually, before we do that, I just want to make sure that you're not super confused about the E step. So the E step is we compute E step. Compute P of Zn given Xn, right? And this is equal to 1 over the square root of the determinant of 2 pi sigma z given x, right? Times e to the negative 1/2 z n minus, z has a mu of 0. Actually, now this is different because it's z given x, so it's not 0. We have sigma z given x inverse z n minus mu z given x. And this is the probability of this thing, right? So we compute all of the zn's and we get like some values, right? So then maybe for each xn, you maybe have like a bunch of zn's that you want to calculate, right? then like what you do is you have Zn on this side and Xn on this side, and then you calculate a table for it, right? And then you put the value inside here, right? Okay. And then what we do to try and compute the expected value maximization in the M step is maximize with respect to, what do we have as parameters here? We have mu, we have this thing, we have psi, right? So we have these three things to compute. And what we get is actually somewhat close to linear regression. It looks like this. This is equal to the optimal value, the star means optimal value of, say, n is equal to 1 to n, xn minus mu, expected value of z given p of z given x, z given x, and this entire thing is zn transpose. And then the next quantity is n is equal to 1 to n, e of z given the same thing as this one, of zn transpose, and the inverse. Okay. This looks really close to the solution for least squares. I'll let you think about it first. But pretty much like the lambdas is a linear function of all the z's. So we want x's to be like representative with these z's. So that's how we have these z's here. And this is the covariance of z given x. And this is the kind of difference, I guess, like the linear mapping of the two, right? Okay, so now after you have these, you can then calculate, you can then like plug it in and get lambda star is equal to the same thing. I'm not going to write the same thing again. See, mu z given x transpose, right? This is actually just mu given, mu z given x transpose, right? Because it's the expected value of the average of zn. And then we have, oh, actually, I said I wouldn't write it again. We have mu z given x transpose plus sigma of z given x, this entire thing to the -1, right? So now you see that this quantity is not d by d, right? If we set hidden dimensions is h, right? H for hidden. This is actually h by h, right? We know that h is a lot smaller than d. So this area will likely never be 0 because there's so little factors. If there's not a lot of factors, that means that the matrix won't be very big, right? If you had a number, say like 3, right? This area is 3, right? Now if you say this matrix will be 3, 0, 2, 0, this will be 6, right? But it's a lot easier to make a mistake and say this is, say, 3, 1, 6, 2. This will give you an area of 0 because it looks like 3, 1, and 6, 2. Okay? So that's why with the smaller dimensions it's harder to screw up. And so that's why factor analysis is used for when you might not have a lot of data, or if you want to find out the hidden variables that kind of give you the values of everything. Okay? And just for the completeness, we want to give values for mu. Mu is just very simple. It's 1 over m, the summation of xn, n to n. It's just the average, right? That makes sense. And now the phi ii for all I is equal to, this one's kind of long, 1 over m n xn transpose minus xn mu z given x transpose mu lambda transpose minus lambda mu z given x xn transpose plus lambda mu z given x mu z given x transpose plus sigma z given x lambda transpose. Okay, and that's for all the indices of phi. So what you can do is try to make this entire thing first, and then just select the ith index of this matrix. You don't want anything else because you don't want it to become like negative area. So that's why you only keep the diagonals. And that concludes our discussion for factor analysis. The main point you should get from this is that sometimes Gaussian mixture models don't usually work if you don't have enough data. And so what other people try to do is to try and find like smaller factors that determine the values of your outputs. And usually there's less factors than there are outputs. And so it's kind of like a compression thing. And when you compress it, you get more meaningful data inside of your smaller dimensions, which is your hidden latent variables. Okay, thank you.